Thank you very much, ladies and gentlemen. I thought I'd have a few words about the rare earth processing, but taking a look at a South African perspective. South Africa has always been blessed with enormous mineral wealth and almost no capital investment has ever been an issue, really. The deposits were large, the deposits were rich, and it's never been a big problem. The rare earths, however, is a bit of a different thing, and I'd like to just share a few thoughts about where South Africa stands with respect to rare earth production. Okay, I've been fascinated with rare earths for a long time. I did my PhD in rare earth processing many years ago. Not quite like William Brooks. He saw the rare earth elements, perplexed him in our researches, baffle us in our speculations, and haunt us in our very dreams. They stretch like unknown sea before us, mocking, mystifying, murmuring strange revelations and possibilities. It sounds really interesting. For me, on the other hand, I've always been a bit frustrated with the rare earths because they are so similar and so difficult to separate. I never had these beautiful thoughts about rare earths, but anyway, rare earths have a large number of very interesting applications, and obviously it is a hot topic for South Africa as well. So I thought, let's have a look first. What are the rare earth elements? Essentially the lanthanide series of elements. Unlike normal series in the periodic table, the lanthanides actually stick out. So they would actually stick out towards us. They don't run across like that. Okay, so there they are, 15 of them, sitting there and causing a lot of interest at the moment. I think Annelies also had the slide on earlier. It is from the US Geological Survey. The name rare earths was coined in those years when. And I think it comes to one of your definitions also. It was very difficult to isolate, difficult to see, so people thought they were rare. They are actually not that rare at all. If you look at that circle there, they are about at the same abundance as copper, nickel, cobalt. And that certainly isn't really regarded as rare. In fact, cerium is the 25th most abundant element at 68 parts per million in the Earth's crust. So the rare earths is a bit of a misnomer. So where do we actually find them if they're not so rare? Where are they? In fact, they spread really right across the globe, right across the Earth's crust. Not really concentrated in many places. Enrichment is normally a hydrothermal process where you have this concentration through hydrothermal processes in certain areas. There's also a reason why the rare earths do not occur by themselves, individually. They always occur together. There are a couple of large resources, like you can see in China, Brazil and the US, but for the rest, it's pretty much spread through the whole world. I've got a picture there of Bayan Obo, the world's largest rare earth deposit, by a long shot in China. And on the other side is an aerial picture of the area where you could see just the environmental damage done through the exploitation of that deposit. It is truly enormous. There's nothing like that on Earth. And that would also, I suppose, explain why China is so dominant in the rare earth space. It is a truly world-class deposit. If you look at that, you can see what impact China really has on the rare earth industry in the world. China possesses only 40% of the world's reserves of rare earths, but they produce in excess of 80%. Some analysts feel even up to 95% a couple of years ago of the world production. So they don't have all the rare earths, but they certainly produce most of them, and therefore they have a very strong lever. In July 2010, the Chinese Ministry of Commerce restricted rare earth exports to the rest of the world, and immediately the prices of rare earths shot up by excess of 1,500%. You can see on the graph on the side, the prices simply shot into the air. In 2013, they relaxed these quotas again, and the rare earth prices relaxed right back to where they were before that. So it shows you that China can basically, by opening and closing a tap, affect the price of rare earths dramatically. So this has obviously scared a lot of people in the world, many countries, the US, Japan, Europe, and rare earths in many cases were declared strategic elements. And there was obviously a big drive after that to get away from the dominance of China as a source of rare earth elements. Especially with the development of green technologies, rare earths became very important, and the world just couldn't afford that China would have total control. So there was a big drive. There are two other refineries at the moment operating in the world outside of China. Lynas is the one in Malaysia. It is probably the largest and most modern rare earth refinery. And then Mountain Pass of Molycorp. Molycorp has since gone under after the drop in price. So the Mountain Pass operation has been mothballed, but it probably could be started up again relatively easily. So the big driving force for rare earth production is not so much a financial one. It's not so much driven by the cheaper alternative, but more from a strategic perspective. So the world is prepared to take rare earth production that's even more expensive as long as it's safe and secure and not controlled by China. So outside of China, there are two other world-class deposits. The one is the Mountain Pass in the USA, with anything from 2 to 4 million tons contained REO. And then there's Mount Weld in Australia. Mount Weld is the single feed for the Lynas refinery. It's quite a new deposit, and it's also got close to 1.5 to 2 million tons of contained REO. So I guess the next step is, what about South Africa? Do we have rare earths or not? We've got so much of everything else. Do we have rare earths? The short answer is yes, we do. But they are not so well developed. It's not such world-class deposit as we are used to with all the other minerals that we have. An interesting one is a vast surface resource of rare earth elements in the phosphogypsum dumps in Richards Bay and Palabora. You can see them there. They are truly enormous. Millions and millions of tons of phosphogypsum sitting on top of the earth, running at 0.4% rare earths. So that is an enormous resource. But again, very difficult to recover the rare earths from. Another significant resource that South Africa has comes from the mineral sands industry. The monazite that is contained in the heavy mineral sands. The monazite is the waste material from the zircon recovery process in the processing of heavy mineral sands, and so it's essentially a waste product that contains rare earths, although fairly low grade. Big problem with the monazite, as you can see in the formula, there's a thorium in there, and that is a major problem. It's radioactive and presents quite a bit of a problem. Then we have Steenkampskraal. This is the richest rare earth deposit on the globe. It can run up to 26% rare earth oxide. It was initially started as a thorium mine in the Western Cape, and it has a modified Monazite-apatite-quartz and contains up to 26% rare earths, but heavily polluted, obviously, with thorium. Unfortunately, the Steenkampskraal is a relatively small deposit. Only 40,000 tons contained REO is the latest estimate. Then we have essentially the big daddy of deposits in South Africa, Zandkopsdrift, also in the Western Cape. This is a carbonatite deposit, and it has roughly 1 million tons of contained REO. And then there are a lot of pegmatites in Albumspruit area. They also, unfortunately, low grade, but there are quite a few of them, small pockets of pegmatites. So which of these minerals are actually significant for recovering rare earths? The big ones is the bastnasite. They're normally carbonatites like Zandkopsdrift, or the monazites, or xenotime, which is a special one containing the heavy rare earth yttrium. Then there are several minor rare earth minerals, as you can see there. These minerals are normally either very small deposits or they are very low grade. So the big focus has been on the bastnasite, monazite, and the xenotime deposits. For instance, Mountain Pass is a very typical bastnasite deposit. Okay, so if you've got a rare earth deposit, so what are the products that you would really target from such a deposit? Well, there could be a lot of approaches that you can follow. You can either just concentrate and sell on the market. You can do a chemical concentrate and sell that. As you can see, the value increases more and more. But in the end, the big value lies in separating the rare earths from each other, so that you can make specialist alloys and for specialty applications. So the big drive is always, once you have a deposit, is to finally get all the rare earths separated from each other. It doesn't really serve a major point to sell concentrates. The value that you get for that is very low. So there are a number of established processes for processing rare earths in the world. I've just listed two main ones there, the bastnasite type ores, or the monazite xenotime type ores and concentrates. That's how you would process them. But basically you can divide it into a number of main activities in such a process. It is the cracking of the ore matrix. First you have to crack the matrix so that you can expose the rare earths to get it out. Then you can solubilize or leach them, the rare earths. And then you obviously have to separate the solid from the liquid once you've leached the rare earths. And then you've got to purify it, because a lot of impurities like aluminium actually follows the rare earths through. So you have to purify them. So those are the main aspects of the treatment. Okay, so we've established now that rare earths are valuable, but that they're also not very rare. And then Mariano in 1989 said, but their extraction as pure elements require a higher technology than the winning of gold. Now for me, that's about the understatement of the century. Gold is very simple to extract and process. The rare earths, another story. And the reason for that is really the enrichment process, the concentration processes that happened in geological time, which resulted in very, very complex mineralogy. And it's very, very difficult to upgrade the rare earth minerals physically. Because the rare earths have sort of filtered in between other minerals and completely intergrown into the matrices, very difficult to separate physically from the ores. So very difficult to concentrate. So you end up having to treat the whole ore, which becomes messy and very expensive. Okay, so why are these rare earths? We know they've got difficult mineralogies, but they're also very difficult to process. So why are they so difficult to process? That's the next question I suppose we can ask. Now, if you look at the periodic table, you know the periodic table is built up by the so-called Aufbau principle, where you add different electrons and protons to the elements as you move across. So for the rare earths, this is the rare earth result as because of a gradual filling of f orbitals, which is very interesting in themselves because they are extremely directional orbitals. So the electrons in those orbitals are not shielded by other electrons in the underlying layers. So they are exposed to the nucleus very directly. So the effective nuclear force on a F electron is very high. So what happens is, not like you normally see in the periodic table, that as the atomic number increases, the element becomes bigger and bigger. It actually contracts. So this is a phenomenon called the Lanthanide Contraction, which is a blessing and a curse at the same time. So if you look at that then, you can see that basically the rare earths or the lanthanides, the chemistry is really determined by the ionic radii, and they're actually getting smaller. The second thing is because the f orbitals gets filled up and they are exposed to the nucleus, the valence state is almost exclusively 3. So what does that mean for us? That means for us that the number of f orbitals electrons, we have a number of f orbital electrons which are interesting in itself because of the nature of the f orbitals. So we have a lot of unique characteristics of rare earth elements. There are unusual spectrographic properties. We have a large number of unpaired electrons in the rare earths, and this is why they are so sought after in magnetic materials. And they also have a large magnetic anisotropy, and therefore you can make powerful magnets, permanent magnets from them. And another interesting thing is they form complexes with very high coordination numbers.